is just like nothing but it's same as counter. It's running or it's working based on the registers. So 16 bit counter means it's nothing but it has 16 levels and it's using 4 bits. So we can calculate the number of registers based on the levels. For example, 2 to the power 4 is 16. If you go to like a 2 to the power 2, then it's going to be 4. Or if you use 2 to the power 3, then the number of levels is going to be 8. So it means it will count up to 8 and it will use 3 registers. And here it will count up to number 4 and then it will use 2 registers and so on. So these registers are really, for example, here we have 4 bits and then 16 levels. So this is the register 1, R1, this is R2, and this is R3, and this is R4. So we have 4 registers. And this is actually, this is really counting based on the clock cycles or the internal clock generated by the oscillator inside the microcontroller. So each microcontroller has its inbuilt oscillator that will generate clock cycles or clock pulses. So in the clock pulses, we can configure either it can be the counting should happen at the rising edge of the clock pulse or falling edge of the clock pulse, or you can also select rising edge or falling edge. Okay, so different timers are used in microcontrollers. So they can be 8-bit or 16-bit or 32 bits. So these all are different timers. In microcontrollers, these are peripherals actually. So they have more than one timers in the L476 microcontroller. Similarly, if you take even the other type of microcontroller, the same. So there are so many timers available in each microcontroller. Okay, so this one we had seen already in 8-bit up counter. The maximum value in register is 255. Then because this is 8-bit counter, so 2 to the power 8 is equal to 256. So, but if you count from 0, then it will end up in 255. So this is for 8-bit counter. So it's using 8 registers and 256 levels. So here we get seen the other way. So 4 bits and then 16 levels counting. Okay, so then the value will overflow at 0 to 0 again. So after it reaches the maximum counting 255, then it will just go back to 0 again. It will start to count 0, 1, 2, 3, and so on, 255. So for example, in 8-bit up counter, the maximum value in register is 255. So it means all the 8 registers will have bit 1, 1, 1, 1, 1, 1, 1, and so on. So I mentioned about last week or the week before last week, how can we count the decimal number? So 8421 is the code. And if you want, now this is only for 4 bits, but we have 8 bits here. So how can we do that? So 8 2 times, that is 16. And here this bit position value is 32. And this bit position value is 64. And this bit position value is 128. So now you have to calculate the decimal value based on the bit value. So 0 multiplied by 1 plus 0 multiplied by 2. So if you add like that everything, then you will get the decimal value. So for example, here I mentioned the maximum value in the up counter with 8 bits is going to be 255. So now how we can get this one? So now you can see here in all registers, the bit value is 1, 1, 1, 1, 1, 1, 1, 1, 1. So you have to just multiply this with this the position values, and then you add everything, then you will get 255. For example, now we can try that. 128, 1 multiplied by 128 is 128, plus 1 multiplied by 64 is 64, plus 132, that is 32, plus 1 and 16 is 16, plus 1 and 8, 8, and then 4, and then 2, and then 1. So you add everything by yourself, you will get this number. Okay, so this is just so after the counters finish, all the registers become 1, then all registers will be reset to 0 0 0 0 and then start counting again from up to down. So whenever the register, all the registers is going to get reset to 0, then that operation is called overflow. So this is the maximum these 8 registers can count, and then 255, then all register will go to 0 0 0 0 position, and then it will start counting again. So this is called up counting because this is going like in the upper level 0 1 2 3. And similarly for down counter, the minimum value is in register is 0. It means it will start to count from the maximum value and go towards the minimum value. So this is 255, 254, 253 and so on, and then finally it will reach minimum value, that is 0. So once all registers become 0 0 0 0 0 0 0 0, then we need to reset all the registers to 1 1 1 1 to the maximum value. So just like here, then it will be 255 and then it will start to down counting. So this is the timer function actually. So you can use either down counter or up counter. Sometimes we can use the same 8 registers. You can use it either up counting or down counting based on your application. For example, in your mobile phone, you have the alarm clock function. So if you go to the tab, you have several options. You can use the timer or you can use the alarm clock. You have a stopwatch. So there are several options. These all are really based on these registers. So these all are digital circuits, and digital circuits are registers, and registers are based on flip-flops, and flip-flops are based on logic gates, and the logic gates are based on transistors. So it's like we are building one on another. Okay, so timing diagram. This is the timing diagram of the timer. So it counts from 0 to 255, 2 to the power 8. That is equal to this value. And you can see single count in counter register is equal to single time clock. So here you can see this is time clock and this is the counter register. Just let us start from 0. So this is 0, and whenever this timer clock, this is a 1 clock pulse, 1 complete timer clock. So this is on time, this upper part, this is logic 1, and then this is the lower part, this is logic 0. So this is indicating 1 duty cycle. So for 1 duty cycle is equal to 1 counting, this is 0. And the next clock cycle, we have the another counting, then there is 1. And the next clock cycle, and this is 2. So on, so on. So for each clock cycle, the counter is counting 1 bit. So and then once if it reaches the 255, then it will become 0 again, and so on. And when so whenever it reaches the 255, it resets these all the registers to 0 0 0 0. That is the counting number 0. So at the time you can see the overflow. This flag is going logic high, and then it becomes 0 again. So then again, whenever it reaches 255, then this flag will again go logic up, and it means like this is enabling all the registers to reset, and then it will go back to 0 again after reset. Okay, so here you should know some simple formulas. So one timer count is equal to 1 divided by timer clock frequency. So let us say timer clock frequency. What is timer clock frequency? So each microcontroller has its own clock speed. So this is the microcontroller. If we talk about L476, the one you are using in your final project, so the maximum clock speed, if you look at the data sheet, it's 80 megahertz. But if you talk about the F103, another microcontroller family, so the maximum clock speed is 72 megahertz. So each microcontroller has its maximum system clock speed. So the performance is really based on the clock speed. Okay, so here, so you have to use always this maximum clock speed as the timer clock frequency. So we can call this a F timer clock. So it indicates timer clock frequency. So here we are talking in this example about this microcontroller. So we are talking about the timer clock frequency is the maximum value is 72 megahertz. So then the counter period is 13.88 nanoseconds. How I got this value? So here you can see the formula. Counter time period of the counter is equal to 1 divided by the clock frequency, that is the system clock. So here you can see 1 divided by 72 megahertz, that is going to be 13.88 nanoseconds. So now you can also calculate the T overflow. So we had seen here underflow and overflow. So here it's overflow and here it's underflow. So after it reach this minimum number, it's going underflow and then resetting this. So here this T overflow is equal to 13.88 nanoseconds. That is the timer of the counter. And then you can see also there is a timer count. So this timer count multiplied by the number of levels. So this is the 8-bit. This is the 8-bit. So the number of levels are 256. So you have to multiply this time with these levels. Then you will get the overflow time period. So here it's 3.55 microseconds. So maybe you try to remember this. This is the simple formula to calculate the timer of the timer count based on the frequency of the microcontroller, and then you have to count the overflow timing as well. Okay, so when you configure timer, you should configure pre-scalar period. So I think a couple of weeks ago I mentioned about I will talk about pre-scalar later. So this pre-scalar value is very important because we can change the pre-scalar value whatever we want. This pre-scalar value, what is the use of this pre-scalar value? Pre-scalar value is really helping us to slow down the timer clock frequency. So let us see here in this example. So in this example timing diagram, you can see pre-scalar value is set to 2. Because of this, what is happening here? So 2 means what? So I am setting up 2 internal clock as a 1. So for example here, this is the logic 1 and this is logic 0. This is one complete clock cycle. And this is another complete clock cycle is repeating. So if I set this pre-scalar value is equal to 2, this will consider these 2 as a 1. So it means the counter will count for every 2 internal clock cycles. So here you can see this is the counter register is counting. So for example, here it's number 1, decimal number 1, and then it's not changing immediately after ending up this one. So it's considering 2 complete clock cycles. So then this is equal to 1 counting. So this is number 2, and then it's taking another 2 clock cycles from here to here, and then it's counting to the next value 3, and so on. So we are setting up this instead of for every clock, every single clock, internal clock, we are making 1 counting. Instead of doing that, we are making the single counting for every 2 clock cycles. So in this way, we can slow down that. So we can see that with one more example, then you will understand, I think. You can see the formula. The formula, what is the formula? We know already the formula. The timer count is equal to 1 divided by internal clock frequency. That is this formula. Timer count is equal to 1 divided by the timer clock frequency. So the timer clock frequency is the maximum clock speed of the microcontroller. So this is for pre-scalar value is equal to 1, because here we are counting whenever the internal for every single internal clock. So here we have just only 1 clock is equal to 1 counting. So this is on time, off time, and this is one single counting. But here you can see pre-scalar value is set to 2. So it means for every 2 clock cycles, we are making counting 1. So here, what is the formula? So this is the formula. So T counter is equal to N divided by F internal clock. So this N is the pre-scalar value that you are setting up. So in the previous example, I set 2 as the pre-scalar value. So here n is equal to 2. So in this third example, I set up the pre-scalar value as 7,200. So it means like for every 7,200 clock cycles, this counting will be 1. So let us see here. The formula is, this is the formula. So now T counter is equal to n divided by frequency of the internal clock. That is the maximum clock speed. So here is 7,200 is the pre-scalar value, and then divided by 72 megahertz, that's the maximum clock speed. So then I get the T counter period as 0.1 millisecond. So now once I know this value and also I know this number of levels, then I can calculate the T overflow, the time period for the overflow. So that is equal to this value multiplied by the number of levels. If this is the 8-bit counter, then 2 to the power 8 is 256 that we know. So we are just multiplying this, then that will be 25.6 millisecond. This is for 8-bit counter. The same if I'm going to use 16-bit counter, then what will happen? 2 to the power 16 is equal to 65,536. So then you have to just multiply the same timing with this number of levels, then you will get the T overflow timing. So this is a simple calculation. So based on the number of bits, this is going to be different because in each microcontroller, we have different number of bits timers. So the time overflow will be different, or overflow timing will be different based on the number of bits. This is a very straightforward and simple formula to remember to calculate this, and then based on that you can calculate this overflow.